Hello everyone, I am Zach Peterson. Welcome back to my channel. If you're on social media, you probably follow me on LinkedIn. You do follow me on LinkedIn, right? And you've probably seen me on the Altium Academy channel. You are subscribed to the Altium Academy channel, right? And if you've seen me in either of those places, then you know I like to bitch about a few specific topics. Ferrite beads, split planes, and AI. Today we're gonna talk about that last one, AI, and specifically its use on social media to talk about all sorts of strange PCB design topics. Let's go ahead and jump in and get started. Now, I know I'm going to use this video to complain about a particular usage of AI, but I want to make sure that everybody understands that I'm actually a fan of AI and I think it does some really cool things. I've worked with companies that are using AI for PCB design and analysis, such as Celis and Dempaflux. I've talked to tons of CEOs and engineers who are building AI products on the Altium On Track podcast, and I think it has a lot of great potential to make our lives as engineers a lot easier. There are also multiple areas in my business where I use AI, and I love it because it's given me back a lot of time that I can spend with my family, and it's helped me make some extra money and do things that I wouldn't normally be able to do. There are also some things that I have to do on a daily basis that make me want to introduce my laptop to a hammer, and AI has helped me automate some of those tasks, and now I don't hate my computer as much. But my biggest gripe with AI is not any of those things with automation that I just mentioned. It is actually when people use AI to pretend to be experts on technical topics. And for some reason, this is especially problematic in the area of PCB design. When I say it happens in PCB design a lot, I really do mean a lot. I feel like it's almost every day that I see somebody posting something on LinkedIn that's full of emojis, they don't even proofread it, full of M dashes, it has all of the hallmarks of AI generated content. And just recently, I encountered one of the most egregious examples of AI-generated PCB design content that I have ever seen. So that's what we're going to look at in this video. Let's go ahead and jump in and get started. So here on screen, I have a post from Wei Zhang, and this post is all about AI server design and designing the PCBs for AI servers. So here you can see he's talking about, or trying to talk about, designing 2000 watt power and 112G SerDes implementations on AI servers. So let's look at some of the design guidelines here just very briefly, and I'll come back and cover these in detail and explain why most of them are incorrect. So here he talks about the power sag problem, like DC IR drop. He talks about glass weaves. Here he talks about stub resonances, and then he talks about split planes. And then finally, he's talking about warpage. And then he included this image, what he claims to be an AI server PCB, in this post. And you can see that right here on screen. So what I want to do first is just look at some of the comments on this post, and then we're going to go back and look at why this post is total bullshit. Now, I originally posted a comment on this post, but unfortunately it got deleted. I was pretty harsh in that comment. And there were a lot of people in my replies who were frankly agreeing with me wholeheartedly that this post is total bullshit. There are some other folks that call out this nonsense here in the comments section. Sakandi Tony writes, "The image is grade 10, the guideline is grade 2. This is basic, nothing about it is 112G, clearly you don't know what you're talking about." Now Wei replies, "Thanks for your honest feedback, Sakandi. You're correct that the example image was simplified to illustrate a foundational concept," and then he goes on and on like this. But if you read through this reply, and if you've ever read any sort of AI generated content on ChatGPT, you will immediately pick up that this reply was written by ChatGPT. So not only is this guy using AI to generate the bullshit design guidelines at the beginning of the post, but he's also using AI to create his responses to these comments. Fabian Kemp writes, "These emojis are so annoying." Wei replies, or I guess I should say ChatGPT replies, "Fair point, Fabian, M dash. I'll keep that in mind for future posts and aim for a more neutral tone. Thanks for the feedback." Like, it's just sad, man. Just admit that you got it wrong. Now, as I continue to scroll through here, you're going to see that there are some other PCB pages that jump into the comments and use this as an opportunity to advertise their products and services. Here, PCB Equipment writes, top-notch AI server motherboards from design and development to production and final practical application cannot do without the most crucial PCB equipment. This is a hallmark of what Chinese equipment manufacturers and PCB manufacturers do. They use every possible opportunity to advertise their products and services, and it's just such a major turnoff. Right below it, we have a reply from PCBA Components Assembly Rich Full Joy Electronics. What kind of company name is that? Anyways, it looks like they put two AI generated responses into the same reply. And of course, they're overly positive. They're using the M dash, and they're basically ending with like a positive note with this all about mechanical balance point. This is a highlight of ChatGPT generated content. And right below that, we have a reply from Stuart Somerville, who is, of course, better known on the Altium Academy channel as Superfan Chromatech, who has summoned me from the depths of hell to deal with this nonsense.
We're free!
Right below Stuart's reply, Ron Frank writes, this is a great example of how AI can be misused to disseminate erroneous data for personal gain. Reading through the comments, you see individuals with higher levels of learning and experience, subject matter experts, easily seeing through the holes in this report. Couldn't agree more, Ron Frank. And right below that, we have another Chinese PCB company using this as an opportunity to post their AI-generated marketing nonsense as a reply on other AI-generated marketing nonsense. This is some Inception shit right here.
How do I know you can deliver?
You don't. But I can.
And if we keep scrolling, we see even more Chinese auto-generated marketing nonsense posted as replies on the original Chinese AI-generated marketing nonsense. And finally, Alex Tarasov writes, it looks like 6U VPX. I don't think it is connected with AI and has 2000 watts power dissipation. Very astute, Alex. I'm going to address that here shortly. Now, aside from these Chinese companies and pages coming on here and adding their marketing nonsense to the original AI-generated marketing nonsense, I'm glad to see some actual human PCB designers jump in here and call this out for what it is. It's really helping to restore my faith in humanity. What I want to do now is go back up to the original post and take a look at those 5 design guidelines, and we'll really see how applicable they are to the case of AI servers with 112G SerDes links. So here we are back up at the top of this post, and I just want to zoom in and look at each of these guidelines individually to see where the problems are. Now, the first dead giveaway, or what should be a dead giveaway, that this is AI generated, is the fact that it's a list of 5 points. It's full of emojis, which is what ChatGPT will produce if you tell it you're creating social media content. And then it also uses the word pitfall everywhere. I've never met an engineer that uses the word pitfall ever, but apparently ChatGPT thinks that engineers use that word all the time. Now, item 1 in this list is the power sag pitfall, or DC IR drop. Now, it is true that IR drop happens when you have DC current going through a conductor. You do lose a small amount of voltage, and as the length of that route increases, you lose more voltage over a longer distance. Now, that is one of the reasons that we use planes. It's because we can get a much higher current carrying capacity than if we were just to use a simple trace. The other reason that we use planes is because we want to have the plane that's carrying our power very close to our ground plane, and that provides a lot of decoupling capacitance at very high frequencies, also known as plane capacitance. This is how you ensure low PDN impedance and thus stable power delivery from the 100 megahertz range up to about the gigahertz range. Once you get into gigahertz frequencies, the PDN structure on the chip itself actually takes over and becomes responsible for providing stable power. Here, this guideline doesn't say anything about power stability, it just talks about IR drop, and then the recommendation is to use 2 ounce to 3 ounce heavy copper on the internal core rails. A much better guideline is to just use more plane layers rather than trying to pack all the copper onto a single plane layer. The reason is that that copper becomes more difficult to drill and etch as it gets thicker, so it's preferable to use more copper on more planes rather than packing it all as heavy copper on a single layer. The other issue is with via formation. Once you have heavy copper, you're going to be limited in the diameter of vias that you can form coming into that plane layer. And that's important because at 112G, you're generally operating with a BGA that is less than 1 millimeter pitch. That means your drill diameters are going to get really small because you're using these thin layers, and that's because you're using blind and buried vias in order to get power and signal into that BGA for that processor that has your 112G interface. The other thing he mentions here in this guideline is to avoid neck downs near the BGA pins to prevent localized overheating. This totally contradicts the use of planes in the internal layers. So you might be asking, what is neck down? Well, neck down occurs when you're routing a trace into the pins in a BGA, and you need to reduce the width of that trace in order to route between the pins. Here I have an image pulled up on Google Images, and you can kind of see what I mean just by looking at this image. As this differential interface routes into the boundary of this BGA, you have a rule that automatically reduces the trace width so that you can put the traces in between the pins on this BGA and then route to your destination. But here's the thing, if you're routing power on a power layer, you don't need to do any routing using traces to get power into the BGA. That's because all of the pins that contain power and ground are generally in the interior region of that BGA. So you're not going to be routing a trace in from the outside. Instead, you're going to be using vias to connect those pins directly to the planes on the internal layer. So in short, you would never use neck down routing for power, but of course AI thinks you would because you have to route the power into a BGA. Let's look at the next one. The next one says the glass weave pitfall or signal skew. Here it says at 112 gigabits per second, the physical texture of the PCB can destroy signal timing, which is a true statement. Here he says that the fix is to specify spread glass, such as a 1067 weave, to ensure a uniform dielectric constant. He then says use zigzag routing, rotating the layout by 10 degrees so the traces don't, by chance, run parallel to a single glass fiber. And then he says use ultra low loss materials like Megatron 8. What the AI has failed to realize is that Megatron 8 is already built on spread glass, so all this other stuff kind of becomes meaningless. Also, if you do use spread glass, you don't really need to use zigzag routing. And finally, the optimal rotation for zigzag routing is to rotate the artwork by 15 degrees, not by 10 degrees. All of the advanced materials that are used to build AI servers and to build the chip substrates that are used for all the processors are already using materials that use spread glass, or in the case of the newer resin-coated copper materials, there's no glass at all. This illustrates a great example where AI takes a truthful statement, but it misses all of the context around it and then puts it out here into a social media post as if it's the best current information. Next, number 3, the stub resonance pitfall, or via reflections. What's interesting about this is that the stubs don't create via reflections necessarily, it's that they create a reflection which destructively interferes with the incoming signal and then creates a big dip in the insertion loss. But forget about the physics for just a moment. Let's just look at what is written in the post. Here it's written, in 20+ layer boards, unused via stubs act as antennas that choke data flow at high frequencies. Now it is true that via stubs become lossy elements at high frequencies, but it's not because they're antennas. They act like quarter wavelength or fractional wavelength terminators at specific frequencies. Also, it says that this happens in 20+ layer boards, but really the layer count doesn't matter. What matters is the length of the stub, not the layer count. Next, it says the fix is mandatory backdrilling for all signal vias above 10 gigabits per second to remove parasitic stubs. Or you could just route all the way through the stack up so that there is no stub, or a very small stub and it puts those resonances up to very high frequencies that are beyond your required channel bandwidth. The other thing you could do is what's listed here in the second fix, which is the correct guidance. The fix is to use blind and buried vias HDI technology to eliminate stubs entirely in high density areas. Or you could just do it everywhere, not just in the high density areas. Number 4, the split plane pitfall. Crossing a split in the ground plane creates an inductive loop that screams electromagnetic interference. I think the AI decided to plagiarize that from some other article somewhere on the internet. Regardless, it is true that you should use a 100% solid reference plane, as is listed right here in fix number 1. But anybody that's designing at these frequencies knows that you're not going to start splitting up a ground plane for any reason other than to include an isolated DC-DC converter on the board. And even then, you don't do that on AI server boards. There's a dedicated power supply that has the isolated DC-DC converter. So because of that, this type of guideline doesn't even provide any value on a list about AI server design. And next, warpage, the warpage pitfall. Here it says, massive AI boards can bend like potato chips during reflow, cracking solder joints. Now this statement about bending like potato chips during reflow is something that I've actually read in multiple other places on the internet, so there's some plagiarism going on here. But it is true that excessive warpage or extreme warpage can crack the solder joints, but it can also cause damage to vias. A bigger issue in these types of designs is not just solder joint cracking, it's actually warpage that leads to non-planarity in the BGA region. Because if you have non-planarity in the BGA region, the BGA won't be able to solder down fully onto the PCB. That can result in defects like head and pillow, or it could even result in via cracking coming into the BGA. Here it lists the fix as using underfill for large BGAs to reinforce solder balls against thermal and mechanical stress.
You sure about that?
This may have been true in the past where we tended to only use large pitch BGAs, but at the fine pitch BGAs that are needed in these types of systems, what you should actually do is use more advanced materials that have their CTE values matched closely to copper and the solder ball and to each other between the chip package and the PCB. There are other reasons to use underfill, but the reason listed here is not to solve any problem. It's really just listed as a band-aid solution. And finally, let's look at the summary. Here he says, success in AI hardware is all about simulation first design. What's interesting here is that none of the other design guidelines had anything to do with simulation, so I don't know why this was listed. And then he says, ensure your power integrity feeds the chip and your signal integrity lets the chip be heard. Very ChatGPT. Here's another dead giveaway of AI generated content on social media. It's the hashtags. Take a look at all of these hashtags. They're all written in title case. That's a dead giveaway that ChatGPT wrote these hashtags. Now the next thing I want to look at in this post is not the design guidelines. I actually want to take a look at the image here of this supposed AI server. Now remember what one of these comments said. Here we have from Alex Tarasov. It looks like a 6U VPX. I don't think it is connected with AI or that it has 2000 watts power dissipation. And Alex is absolutely correct. Let's go back to this image here. Now, if this were actually an image of an AI server, I would expect things like PCIe card slots. I would expect maybe a display port or a couple of display ports. I would definitely expect some SFP cages so that we can slide an optical transceiver into the back of this server. But take a look at the image here. What do we see? Well, here we see what looks like two RJ45 ports, and you can tell that these are RJ45 mag jacks because you can see the little nubs where it mounts into the PCB, and then below it you have a set of 1, 2, 3, 4, 5, 6, 7, 8 pins coming into the back of the connector. This is exactly the structure of RJ45 connectors, and those 8 pins are for your Ethernet signals. Now, if you look across the front or the top side of this image, you don't see any SFP cage, and you would definitely expect to see an SFP cage for an optical transceiver on a board that has 112G SerDes for AI compute. Now, what else do we see in this image? Well, over here on the left side, we see what looks to be a D-sub connector. Now, how do I know that this is a D-sub connector? Well, first you have the shroud that protrudes over the top edge, and then you have the 2 posts that then hold this connector onto the PCB. And then you can see all of the pins or the holes lined up right here in between those 2 posts. So to me, that's a dead giveaway that this is a D-sub connector. Now, some servers might have a D-sub connector for serial port access, but typically you don't need it. Now, between the D-sub and the RJ45 connectors, you can see that we have lined up right here what looks like a group of 5 SMA connectors lined up along the top. I have never seen a server of any kind that has SMA connectors on it. SMA connectors are used to connect a coax cable, and that coax cable is generally used for RF signals. Well, why would an AI server need an RF signal? Well, the answer is it doesn't. A lot of servers don't even have Wi-Fi built into them. They access everything through a network connection that's done over copper, such as the RJ45s, or in the case of an AI server, it would be over a fiber connection using an optical transceiver. But of course, we don't even see that on this board. So clearly, this board is not an AI server, or really any server of any kind. How do we know that it is a 6U VPX card, and, well, what is a 6U VPX card? Well, there are two things that are a dead giveaway that this is a 6U VPX card. And the first thing is this arrangement of holes and guide pins along the back side or the bottom side of this image. Here you can see all this arrangement of holes that are going to be used for through-hole pins, and then here you have these tabs coming off of the back. Well, take a look at an image of this connector. You can see it right here on this 6U VPX Ethernet switch. Here you can see the connector that mounts onto the PCB, and then you can see these holes for these guide pins coming off of those tabs in that image. So this is definitely the point where a 6U VPX connector would mount onto this PCB. The other dead giveaway is the dimensions. Here you can see that the dimensions are 233 millimeters by 160 millimeters. Well, what is a 6U VPX card size? All you got to do is Google it, and at least Google's AI gets this correct. Google's AI says right here that the measurements of a 6U VPX card is 233 millimeters by 160 millimeters. Amazing! Now, VPX cards are defined in the VITA standards, and there are multiple VITA standards that are used to define interoperability and common interfaces and mechanical form factors that are used in military embedded systems. These systems are constructed using a backplane, and then you have cards that slide in and plug into the backplane, and the backplane allows multiple different cards, possibly from different vendors, to then talk to each other using common interfaces. Now, we know that this is an American piece of military hardware because here you can see in the image the primary units for the dimensions are in mil, and you can see that here on the horizontal and the vertical dimension. Now, just for fun, I want to do a Google reverse image search, and let's see if we can actually find out where this image came from. If I just drag this image into Google reverse image search and we click on exact matches, you can see here that this is the only copy of this image that exists on the internet aside from this guy who's some student at a university. And if you look on this guy's profile, you won't see that image, well, anywhere. So that means this Chinese guy somehow got a hold of military technology from the United States and is now showing it on LinkedIn. The only way he could have gotten this image is if he has the original design files, and that means he either stole it or somebody exported it to him without authorization. That shit is crazy illegal here in the United States, and somebody's going to be taking a little trip if the government ever finds out about it.
We're going to federal pound me in the ass prison.
I don't want to go to any prison.
Now, the biggest problem with this post is not the fact that some Chinese guy got a hold of military hardware illegally, and it's not the fact that someone's posting guidelines without context. It's the fact that those guidelines could kind of apply to anything. I've seen other people on LinkedIn post those same AI-generated PCB design guidelines about their dumb IoT boards. And the bigger problem is that somebody might see those design guidelines, start repeating them, and then it's going to create this vicious cycle of more and more people continuing to spread bad PCB design information. So if you want the best PCB design guidance, make sure to subscribe to this channel. Make sure to head over to Altium Academy, where there's a lot of other videos featuring me, and make sure to subscribe to that channel, and we're all going to keep putting out the best design guidelines we can. Thanks for watching this video, everybody. Make sure to hit the subscribe button, hit the like button, and go follow me on LinkedIn, and hopefully we can annihilate AI-generated PCB design slop together. I'll see y'all in the next video.